And so, my good friends, notice that the vectors 0, 1 and 1, 0 form a basis for the column space of A. And 1, 0, negative 1 and 0, 1, 2 form the basis for the row space of A. Notice that the basis of the column space and the basis of the row space each had two vectors in it, even though they're different worlds, because one is part of R2 and one is part of R3. But if you think about it, the span for the column space, that's basically the entire plane. That's the entire R2 plane. Whereas the span of these two vectors here is also a plane in R3. It's not the entire R3. It's a plane. It's a plane in R3. Now, you may have noticed that the dimensions of the row space and the dimensions of the column space are both equal. They both equal 2. I'm going to write that down. Dimension of row space of A equals dimension of column space A, which in this case equals 2. And you may say, gee, maybe that's a coincidence. But guess what? It's not a coincidence. Shockingly, it turns out that the dimensions of the row space is always equal to the dimensions of the column space. An amazing theorem, which we are going to get to improve. And that's, like I say, amazing, even though the row space and the column space are totally different worlds, because one's R2, one's R3, yada, yada, yada. But that is an amazing fact that we see. Yay.